Let's talk about cyclohexane. Cyclo, whenever you have cyclo, it means that the molecule is going in a ring, and the prefix hex means you have 6 carbons. So this is going to be a ring made of 6 carbons. And you'd be used to seeing something like this looking straight at the molecule. But there's an important amount of information you can get, three-dimensional information about the molecule, when you rotate it and look at the side of the molecule. So there's a way to draw this, and you can focus on this paper. The way to draw it from the side, there are several different techniques, but you want to draw 2 slanting parallel lines, and right next to each other. The one that is lower, you want to go a little further down. So 2 slanting parallel lines. You can see that this end is going up, so you want to have a dot going down. You can see this end on the right is going down, so you want to have a dot going up. Now, connect the lines to the dot, and that gives you a picture of this cyclohexane turned to the side. So let me see if I can recreate that here. You have this cyclohexane, and you're turning it to the side. Oops, so you can sort of, this way, the way I did it, the drawing was like this, so you can see you have those 2 on the side, one going down and one going up, and it's kind of like that drawing there. If I were to take all the white and green balls off, you'd see how that would sort of resemble the drawing that I made. So you're just trying to look at this cyclohexane from the side. Now, look, in this model, there are 2 things that you want to notice. Look at a single carbon. This carbon has 2 types of atoms bonded to it. One is going straight up, and the other is kind of going to the side. And if you look at each carbon, there's one that's straight down and one is kind of to the side. Straight up and one is kind of to the side, right? You can look at each of those. The ones that are either going straight up or straight down are called axial. It's as if they're on an axis that could spin around. The ones going out to the side, the white ones in this diagram, are called equatorial. Just like the equator straddles the side of the Earth, these equatorial groups go to the side of the molecule. Now, notice, if the axial group is going up, the equatorial is going down. If the axial group is going down, the equatorial group is going up. Also notice that they switch. So if it's going axial up on one carbon, on the carbon adjacent to it, it'll be going down. Axial down, go to the carbon adjacent, axial up. Go to the carbon adjacent, axial down. So that as you go from one carbon to the next, the direction of an axial group switches. Axial up, axial down, axial up, axial down. The same thing happens with equatorial. If you have equatorial going up on this carbon, on the carbon adjacent to it, the equatorial group is going down. If you go to the carbon adjacent to it, equatorial is going up, equatorial down, and so on. Now the orientations can flip if, for example, you have a really big group. If you have a really big group in an axial position, each of these atoms has electron clouds around it which are negatively charged. Like charges repel, and so these are constantly feeling a repulsion against each other that makes the molecule really uncomfortable. One of the ways that the molecule can deal with that is that, watch these white groups, they're equatorial now, right? The molecule can switch. The white groups are now axial, and this big bulky group is equatorial. And notice that when it's equatorial, it's much further from all the other groups. When things knock against each other and create a repulsion, the $10 fancy word to describe that is steric hindrance. That's S-T-E-R-I-C. There is less steric hindrance when a bulky group is in an equatorial position. Now these exist in equilibrium, so if you had this molecule, which is ethyl cyclohexane, Most of the molecules will be in the equatorial position, but remember this isn't a fossil, this is a living, vibrating molecule, and as it knocks into walls or other molecules, or as it encounters heat in the environment, it'll vibrate and twist and turn, and sometimes the molecule will switch into the other conformation, and you'll have a small population of ethyl cyclohexanes where the ethyl group is in the axial position. But because of the steric repulsions and steric hindrance, most of the ethyl cyclohexane molecules will be in the equatorial position. So the thing to remember is if you have a cyclohexane, the bulky group will prefer to be, or the largest group will prefer to be in the equatorial position.
That's the most stable.
Because that's the most stable, because there's the least steric hindrance.